Mass and energy balance for biosystem. Module 7. Conservation of energy. Segment 2. Review of energy conservation. Is Me Lily from School of Life Sciences and Technology, Institute Teknologi Bandung. In the previous segment, we already discussed about the basic energy concept, and in this segment, we will discuss about the review of energy conservation statement. The total energy of a system is always conserved. The conservation equation for total energy is a mathematical description of the movement and accumulation of total energy in a system of interest. And the law of the conservation of total energy states that total energy can be neither created nor destroyed, but only converted from one form into an equivalent quantity of another form of energy. Although total energy is conserved and remain constant in the universe, specific forms of energy, such as mechanical and electrical energy, are not conserved. Instead, different forms of energy can be interconverted from one type to another. Consider the system shown in figure beside. The rates of mass entering and leaving the system have associated energy rates. That is the energy rate inlet and also energy rate at output. The energy crossing the system boundary can be in the form of internal, kinetic, and or potential energy, and the rate at which flow work enters or leaves the system depends on the movement of mass across the system boundary. And the rate at which heat is added to the system is denoted by Q. The rate at which non-flow work is done on the system by the surrounding is indicated by the work non-flow. The generic conservation equation is written to account for the movement of total energy into and out of the system by bulk mass transfer and for the transfer of heat and work across the system boundary. And no generation and consumption terms are present since total energy is conserved. And the differential form of the conservation of total energy can be seen in this slide. Since total mass but not total moles is conserved in all systems, the development of the conservation of total energy equation is presented by using mass and mass rates. And recall the previous equation in the previous segment. The rate total energy is defined as the sum of potential, kinetic, and internal energy. And also, it can be seen in this slide. The previous equation can be written as the form as this equation, and also we can write the total rate of work is given as the sum of the flow and non-flow work, and the equation can be seen in this slide. And for the flow work of any particular flowing stream can be written as this equation. Given that the rate of flow work is the difference between the rate of work done by the fluid at the system inlet and the rate of work done by the fluid at the system outlet, so the rate of flow work can be written as the following equation, which is this one is the work flow by inlet, and this one is work flow by outlet, and this one is the sum of rate of non-flow work. So from this equation we can write as the other form as the following equation below. Both specific internal energy and specific enthalpy are tabulated for many conditions. Equations below are the differential form of the conservation of total energy equation that are used most often, and the integral equation is most appropriate to use when trying to evaluate conditions between two discrete time points. Often, the integral form of the equation is used when one or more of the rates of energy, heat, or work are a function of time. Also, for the algebraic form of the conservation of total energy equation is used in situations with a finite time period and when discrete quantities of matter or energy or both enter or leave the system. The algebraic equation can be derived from the integral equation for a defined and finite time period, and the total heat or Q that icon system during the time period is defined as equation below. With this definition, the algebraic form of the conservation of energy equation can be seen in this following equation, where E sees Tf and E sees T0 are the total energy of the system at the final and initial condition. And also the different forms of energy are written in terms of specific energy can be seen in the following equation below. And the substitution for the total amount of work and for the definition of enthalpy result in another common form of the algebraic conservation of energy equation that can be seen in this last equation. Mass accounting or conservation equation may need to be developed along with the energy conservation equation, depending on the complexity of the system. Coupled mass and energy equation are used most often when considering a steady-state system. For the next segment, we will discuss about the closed and isolated system. Until then, I'm Lily from Institute Technology Bandung.